have our second talk today, Sven Krippendorf from Munich, LMU. Sven, for you.
Okay. Yeah, and let me also start by thanking the organizers for putting up together this wonderful program and workshop. It's been a fun time here. Today I will be talking about something which I'm very excited about, and which kind of, is probably relevant at some point to combine with integrability. But if you want to hear about our machine learning work on integrability, please feel free to rewatch the review talk I gave last week. And it's really great to see, actually, after a couple of years, seeing activity in this direction emerging. So today I will be talking about work done over a couple of years. In particular, I will be highlighting recent work which appeared over the summer. So this has been with a bunch of people at various places. Let me highlight some of them, so in particular students involved. So this has been Abhishek, who was a master's student in Munich. He was involved in this early work, and now there's Julian, who's involved in part of the later work and ongoing work in this direction, and he's looking for PhDs this year. So in case you're interested, please take a look at his application. And then there's older work done with Alex Cole, René Kröpsch, Mark Silvery, Valentin, and Gary, and also Andreas, which were in these papers. And Andreas is also involved in all of these efforts, and he's a joint postdoc between LMU and Cornell at the moment. And this year he's going to spend now at LMU. So let's start with setting the scene. So, the underlying physics question that we're interested in is whether we can explore all, in capitals, possible beyond the standard model solutions for the cosmological constant. So that's an ambitious goal, but this has emerged out of something that we a couple of years back we organized a meeting at Microsoft, Physics Meets ML. And so we brought together string theorists and machine learning experts. And one of the questions that we got in the end of the day is, okay, what are the big goals in your in string theory that you want to solve? What are the big problems in beyond the standard model physics? And I think one of them is definitely the cosmological constant. So when we as a faraway goal, can nevertheless put this into a very concrete steps along the way. And the kind of warm-up exercise that I would stress and talk about today is to look at all possible flux vacua with, say, a hierarchically small expectation value of the superpotential. So now let's set the scene a little bit for this problem, and how this connects with machine learning. So when we classically do cosmological constant model building, we often are interested in something like this. So we have some potential, like some scalar potential here. I'm just picking a polynomial. And you want to get some hierarchy involved in, and that you normally can trace to some parameter. And here I just picked it to be a minus b, roughly being 0. So the solution to this, finding hierarchically small things would be to have roughly equal a and b. And this might obviously depend on some underlying parameters in your theory. However, so when we do then model building, often when we do this, what we actually do is we find some exciting mathematical structure that guarantee us this this property. So this can be extra dimensions, this can be symmetries, and so on. So standard thing to think about is thinking about a supersymmetric scalar potential versus a scalar potential in a standard model. And you see the restrictions appearing. So that's a kind of thing we often do. But the nice thing to talk about this, or why to put this into the context with machine learning, is basically if we look on the left-hand side here, is about taking a probabilistic view on this whole story. Namely, when we want to look at some theory space, we typically have, say, some parameters, alpha, and they might be distributed according to some probability distribution. And if you just assume this, you would see that the solutions with alpha equal to A equal to B are not very probable necessarily. So what does it mean in contrast if we want to solve a problem that we do find somehow a different distribution, which singles out highly probable with a highly probable with high probability regions with A equal to B. So I'm stressing this because this is something which we can formulate as an optimization problem and actually address. And so this is really this probabilistic view allows us to look more generally onto the CC. And so the idea is as follows. So typically what we have done, and say if you're thinking about scalar potentials, is we've explored models with few parameters. And we have done this because we have very well established techniques to do this analytically. However, if we think more generally in the kind of cartoon of the space of all models, this is clearly a very, underrepresentation of all of the possibilities that exist. So can we do better? And clearly there is a road, and the road that we systematically want to follow is to follow going from. And this line of investigation is obviously we can formulate here. We can look at models with a scalable number of fields, and this has been obviously looked at often with just statistical physics methods, and but not in a complete way, as I will discuss. But then subsequently, as we have heard yesterday, it's very well known that neural networks are universal function approximators. So by going from this finite number of parameters, we can take a large number of parameter limits in going to neural networks. And so this is an approximator to approximating all possible models in this class. So that's what we want to explore, and that's what we call numerical model building. So to stress why, when you want to go to such general solutions, again, it is highly impossible to look for, do it in a standard way of taking some underlying distribution, because basically, look at this picture. This picture becomes really problematic in high dimensions. So if you go to high dimensional spaces, you will hardly see anything useful appearing. And think about something like an image. If you want to sample randomly from Gaussian some pixels, you would never see a picture of a cat or a dog. Nevertheless, we have generative models around by now that can actually do this. So the idea is here that we do want to learn a probabilistic model to address the cosmological constant. So this means that we have somewhat a map in a sense, so some conditional probability where we can say, given say some desired value of lambda, it generates us, it allows us to sample models that have this property. And this clearly is something which is automatically in the realm of probabilistic model building, and that has a very rich interface with current machine learning. So I think, if you want to go down this route and being systematic about the CC, there's really no alternative to using machine learning. So how do we want to approach this? So the framework we want to look at is a good old friend, namely modular dynamics in string theory. And I want to study those because they lead to very rich physics, and this has been largely unexplored. And there are really interesting discussions that we can have about these spaces. And I think that really stands them out from just looking at something like polynomials, because we can really make an understanding also on our of the physics of these systems. And as a first example, I want to show here results that we have on the looking at the complex structure sector of Type IIB string theory. Good. Let's take a bit of a look of what is the perspective in the literature about numerical explorations of the Type IIB complex structure moduli space. It is largely unanalyzed data that is lying around. So in the sense that we really don't know what is going on in this space. So we have been very productive in constructing actually spaces. So there's a large landscape of geometries. I'm thinking about complete intersection Calabi-Yaus, and I'm thinking about the Kreutzer-Skarke database that we all like to play with. Now, we all obviously are very, hopefully, we have all heard about work that went on roughly 20 years ago from Dan F. Douglas et al. About making statistic statements of flux vacua in these spaces. And there are remarkable statistics statements in these papers, but they do come with assumptions. They come with assumptions such as thinking about looking in the asymptotics only of moduli space and making approximations such as the continuous flux approximation. And given these, we have very profound results about, for instance, distributions of correlation. So in sense of, for instance, of the superpotential. But it states very clearly in the conclusions of this paper 20 years ago, although the ensembles we considered are somewhat crude, we can progress by formulating better ones, which try to reflect more of the structure of the problem and test our hypothesized ensembles against statistics of sample sets of string vacua constructed either systematically or by choosing random examples and doing detailed model-by-model analysis. By finding better ensembles, we will be improving our understanding of the distribution of string M-theory vacua in a relatively concrete way. So this was 20 years ago. And so we can ask, okay, how much have we actually looked at these things? And there are very few explicit solutions that have been looked at. And so in particular, so I will be referring to, a lot, so things that, we did like 10 years ago or so, where we looked at some of these examples here. And they were by far, just giving us a very, very small glimpse of things. And we couldn't really look at ensembles to make statistics. And today, I will show you that we can actually do statistics. So to go to the physics question of addressing the CC or addressing, say, something like small w0, we actually, what are the ways of doing this? If we want to look at all of these ways, we have to be able to look in space and study it. And in particular, one thing which is really, which will become really striking is that these are high-dimensional distributions. So if we only look somewhere in something from given some prior, somewhere where we naively would be looking, we might be missing something. And so what is really crucial is to look into be able to look in the tails of these high-dimensional distributions. And so that's the challenge. So in order to do this, we want to have a tool which can actually address this. So what we want to do is we want to easily obtain flux vacua for a physics question. So this has, we want to be able to do this for many geometries. We want to do this in principle for different regions of moduli space. We want to do different questions. We want to look for supersymmetric vacua and we want to look for non-supersymmetric vacua. And we want to get many samples, so that we can do statistics and that we can use all of these nice machine learning tools to do these dedicated searches and to identify, search in these tails of distribution. And so the framework we put out was in this paper, and I would like to introduce that to you a little bit. Now, let me tell you a little bit about the solutions we do look at, and also because that's kind of giving you the flavor of what these numerical techniques are able to deal with in a nice way. So what we are looking at is Calabi-Yau orientifold compactifications of type IIB to four-dimensional n equals to 1 supercurvity. We focus on the complex structure moduli and the dilaton. And we do know from exciting work in the 90s how to describe this in large, how to describe those dynamics. Namely, we know how the prepotential looks like at large complex structure. So we do have a polynomial contribution, and we have these instanton contributions, which we can calculate all appropriate invariants appropriately. And that's a beautiful story. Now, from this function, you can calculate the scalar potential and superpotential. So the scalar potential is what appears is the standard period vector, which takes the appropriate derivatives of the prepotential, and then you just combine them. The flux potential is the standard Gukov-Witten superpotential, as shown here. So you have 3-form flux turned on. That is here. So the 3-form flux is obviously quantized. And it's always, we have some standard tadpole constraint that we will have to satisfy. Given the scalar potential and superpotential, we're obviously not done. We do want to calculate the minima of this story. And so in this case, you can calculate the standard supergravity scalar potential by taking the appropriate derivatives, etc. And in particular, we will look at two types of solutions, namely supersymmetric ones, so ones where the covariant derivative vanishes, and non-supersymmetric ones where we just minimize this whole beast. Okay, so I'm stressing this because the pipeline that I will show to you is obviously something, if you're thinking about things like Lux pairs, etc., or things that appear in other kinds of mathematical physics. This is something very, this structure can be, transferred. You have to write your dedicated code to do this, but the tools are around. So let me walk you a little bit through how we are connecting with the data, and then how we write our pipeline. So the relevant data for us is given in terms of in the Kreutzer-Skarke database, and in particular, what we want to calculate from each given geometry are the triple intersection numbers and the Gupo-Kammer buffer invariance. And this has been going on. There has been a large program by the Cornell group, where they have written also very nice tools that we are using to actually derive these quantities, namely known as CY tools. And so we're very careful here about how we construct things. So we make sure that we are looking at that we do have a proper orientifold in the game. And for these systems, we can compute all of this data, and using these parts of these algorithmic advances that have been recently proposed in the literature. Good, but so that's a connection with the Calabi-Yau data. Now, as you've seen on the previous slide, the 2 slides ago, from this Calabi-Yau data, what you want to deduce is you can write down the prepotential, and that is essentially the only hard-coded input to our code. Yeah, so this varies between different geometries, and that is what you have to put in. But the rest is pretty much standard formalism. And what we do use is we set up a flexible code to basically calculate all of these things automatically on the fly, and to do this in a fast way. And so let me I want to tell you a little bit about this because this is important for the numerics and all the numerics that you want to do, and in particular if you want to do numerics at scale. Yeah, so this is not something we have a large numerical problem here. So to make these samples, so we have to make our code very efficient. So the first key observation that you might have seen is obviously we have to take a lot of derivatives along the way. So how do we do this? We don't do this with finite differences. We do this with automated differentiation. So this is basically giving you at machine precision the derivatives. This is essentially using old algorithms of backpropagation, because basically you know what the derivatives are, so you can just evaluate them. This is basically similar to what Mathematica is doing under the hood, but it's not simplifying the expression. This is bread and butter when you're talking about backpropagation in neural networks, where you also take the derivatives of these models. Now, this is very easy to implement, and we are using heavily a framework which is called JAX. And so let me try to get this thing. And so to just also to take a little bit away the story of, you know, this is large, this is, you know, you have to go to large coding efforts and, you know, completely throw our favorite our familiar environment of Mathematica around this. So I'm just showing you here, for instance, for the prepotential, which depends on the moduli, how do you implement this triple intersection? Maybe we can get this bar to disappear. But, so you have the triple the standard Yukawa term here. So what is this? So this even knows, so, you know, you write this in standard Einstein summation of this tensor which you have in, and combining this with the moduli. Now, if you're interested in the derivative of this is not something where you have to do a lot of work. It's basically you're taking just the function which is known as like grad in this case, and you do know that you know, you have to tell it that you treat them as complex variables. So you can do this nicely in this environment. So this is all you need. So now this is not making things fast. So now this is basically in Python. And so what you do want to do is you want to make things fast, and this can be done. And basically this is you know, you can just in time compile your code. So this automatically generates C++ code during the first evaluation of the code. And then you have code which is executable not just on your CPU, but also on your GPU, potentially TPU. So this is important if you want to, you know, make things fast. So here's an example on how to do this. And again, this is relatively convenient. So especially once you get used to this. So here's just, for instance, just you know, evaluating a single function here, and you do this you know, a lot of time. So if you do this in the standard Python way, this would take 2 milliseconds. Now, if you just in time compile this entire function and you evaluate it, then you know, you're getting a speed improvement here to 150 microseconds. So this is not parallelizing anything. This is just making your code faster with just one command of things. Now, there's another thing which this does take care of, as is basically parallelizing your computation. And this is also using idle time on a single CPU, essentially of what is going on. And this is basically how to vectorize your code. And so this basically allows you to parallelize your code on a CPU and GPU. And the nice thing about this is that it really avoids manual rewriting of functions, which is typically very rigid and also messy. Yeah, so this is very, very clean, and it can be used very flexibly depending on the purpose, and it leads to huge speed ups. So to show you, for instance, if you are calculating the Hessian, if you're not vectorizing, so you have to go component by component having to calculate this. This took 7 seconds. Now, if you're vectorizing this whole story, again, just using few commands, you are getting an order of, you know, a factor of 100 speed up. So this is huge, right? So, and you have to use these things because you have to evaluate the Hessian a lot of the times. Yeah. So And so you want to do this for a lot of solutions, for instance. Yeah? So you have to do these things. So let me put this into perspective. So if you want to evaluate the covariant derivative of the superpotential, this is for a 2- and 4-moduli example. If you do this in Mathematica, yeah, so you type in the expression Mathematica, these are the curves that you're getting. So, and then you can ask, okay, yeah, now I'm implementing this in Python. This gives you the yellow lines. Now, if I do the just-in-time compilation, I'm getting down. But then, you know, if I combine just-in-time and VMAP, this, you see, gives you an order of magnitude speed improvement to that implementation. And the coding effort is, you know, it's very much overdoable. So this is really like very much, you know, this is like when you work with students can really nicely, this is really very much, you know, very well catered, very well documented to look through this. So you can make a decision of whether you teach your student in Mathematica or at the beginning of their degree, or whether you want to put them into this type of frame. Good. So this is nice. This gives you nice speed ups, but it also, what we made sure of is that we don't write just code which can deal with one problem, but that you kind of are modular in the sense that you can exchange things along the way. So for instance, in the end of the day, you might be interested in different phenomenological properties or different minima, or so that we just replace a part of the code and you can still run everything. And so this is clearly also that to interface with this whole story, there is, you know, we've coded up some things, but, you know, if you want to go to other regions of moduli space, you'll have to just change one of these modules effectively. And this is obviously all ongoing work. But bottom line is you have orders of magnitude speed improvements by using these things. Now let's get started to see how we can look for minima, because we're not there yet. So what you have to do is you have to not just pick fluxes, but you also have to pick starting conditions for your minimizer. And this is something which you know, we do very carefully because it has a huge effect on the performance, as I will show in a second. And again, this is something where, for instance, when we're looking at supersymmetric minima, we can make educated guesses of where these minima lie and what relations between the moduli starting values and the modular values and the fluxes have to have. This we can do. So, for instance, you know, you'd start with your flux vector, which is, you know, in some range, has to satisfy obviously some tadpole constraint. But what you effectively do is something which we call ISD sampling, where you pick half of the flux vector, and then you know, by looking the appropriate matrix here, which is moduli dependent. So we pick some starting points, you know, in some appropriate region within the Kähler cone. Then we can guess the remainder of the flux vector and start close to that. So good. And so what we find with this is that we effectively get much higher success rates, yeah, when we do this carefully. Now, once you've done that, you want to optimize, you want to solve the optimization problem. And so the targets that we do look at is, you know, the supersymmetric one and the non-supersymmetric one. And we've played around with optimizers. And the key thing is, so at the moment, we just use something which is SciPy optimized at root, which works quite nicely. And one second. And so that is something we obviously, you know, are playing with, but for now this works quite nicely, and they're obviously thinking about different optimizers to make things even more efficient. Yes, question. Pardon? This one here. Yes. So basically, you have an expression for the scalar potential, And this comes actually to the next slide as well. So basically, you want to look for minima for this, right? So you have basically, you take the derivative of the scalar potential and put this into your root finding. This is obviously not guaranteed to be a minimum. Then what you have to do in the next step is to make sure that this is actually a minimum, right? So you have to throw away a lot of the solutions. And so this is basically, you know, you have to check that your extremum is a minimum. So this again is putting, you know, you have to put some filters on in terms of making sure that things are okay. So this is having to have a positive string coupling, and we obviously have to make sure that we are that we're just not overcounting due to SL2Z. We have to make sure that our extremum is a minimum. So we look at the Hessian of things. And we have to look that the large complex structure expansion is valid. So for this, we check basically the ratio of these two quantities, namely of the instanton contribution and the perturbative contribution. And I'll show you later, you know, they are really, really tiny, as expected. Good. But so now let me show you a couple of results. So here I'm giving you a result for P1169. So this is a 2 modulus example, and I'm picking this for a couple of reasons. One is I can visualize things nicely to show you things, but also because this has been used in the past. So in 2012, the DAISY cluster with 32 cores and using 100 nodes, so 100 nodes with 32 cores was occupied for 75,000 hours to find for the 25,000 solutions. And now we do this on 4 cores with 5 gigs of memory, something, you know, your laptop or desktop already has. And we do this in 45 minutes to get even more minimum. So this is, you know, this is the kind of speed up that you're getting. Now, let's take a look at this. Let's take a look at these things, because I mentioned that we use these various sampling techniques, and I'm showing you here the imaginary part of the complex structure moduli here, and you can see how these are distributed depending on which kind of sampling method you are using. And if you were to just randomly sample flux vectors and the random starting point in the cone, you would be lying here on these purple points. And as you can see, this corresponds kind of to the boundary of the Kähler cone. So you might see something where you would be interested, okay, everything is lying at the edge of stability of these things. But this is actually not true, because you're just not, with this method, seeing where things are. Namely, if you look at these ISD kind of conditions, you will see very much things appearing within the bulk of this parameter space. And also, you know, you can see how what is the so you can also you know, look at what the distribution with respect to the tadpole is. So the tadpole constraint is shown here. You see, you know, that, you know, they show naively different distributions. You do see now here what is happening with respect to your starting point, these are in gray, and where the optimizer finds the minimum. So you can see again that there are differences appearing based on that sampling technique. So all of these, when we want to do a proper statistical analysis, we have to characterize, etc. But that's something, okay, we can measure, but this is something obviously to be aware of. So there was a question in the chat. Let me see what so the question in the chat is, what is the base sampling techniques most preferred to get such precision at such less time? How is it dealing with the time complexity? Yeah, so in this sense, the results that I will show you are using these ISD sampling techniques. Effectively, that is what we find for the supersymmetric ones to be more efficient. For the ones that I will show you, the non-supersymmetric ones, we actually, the ISD one does not work. And so we have to go back to random explorations. Good. Now, let's look at another example. So this is an example with 4 and 5 moduli. This is something I was involved in, over 10 years ago. And we were happy to have like 10 minima or so. Yeah. So now I said earlier this year, okay, let's generate 1 million for each of these. Yeah. Because with this code, this is now possible. And so this is something, yeah, I mean, Nana might remember, right? So this was at the time I was Bond, for instance, right? So now this is nice because now, okay, we get a lot of these solutions, but we can also plot things, you know, about distributions, yeah, that we do start to see. So we can start to look at, say, how are the values for the string coupling, how are the values for the expectation value of the superpotential, the absolute value distributed. That is shown here. Now, again, so here I think on this slide I have, for instance, you know, if you're worried about stability, there's the contribution of looking at, you know, how stable they are. So this is the measuring the instanton contribution over the classical contribution, and you see that that most of them, you know, your threshold is up here, yeah, something like 10 to the minus 1, 10 to the minus 2 or so, but the bulk, you know, lies very much down here. So these are super exciting. Now, okay, so in this first paper, so we then you know, looked at a couple of geometries to see how far we can push it. So we went up to 25, where we found one, but you see that basically the success rate per starting point and per you know, flux drops with more moduli. Nevertheless, you know, we can still generate large ensembles with reasonable effort. We think we do understand why this is dropping, and this is basically that, you know, the Kähler cone becomes relatively narrow, and so you would have to go to a different phase in order to see where things are going. So that's basically just a, you know, basic geometric fact that we are fighting here. That because also, and the other thing, you know, for instance, like, you know, you can do things also when you you know, relax a tadpole constraint, for instance, and you start finding minima also for things with, you know, 100 moduli, etc. So this is interesting. This is good. Now, one thing that you can look at is how much time does it take to do the minimization, and so this scales very nicely with a number of moduli, right? So here the different colors correspond to different number of moduli. So this is very, you know, not very much putting a lot of time consumer, right? So that's a very good news, right? Because this is like what you know, previously was thought, okay, this is really a bottleneck, but clearly it is not. So now, having these tools around, let me spend the last 20 minutes about exploring and talking a little bit about using them for physics. So coming back to this kind of party line of exploring like spaces, we are clearly in the regime where we're looking at models with a scalable number of fields, and so we want to analyze these kind of models and understand the physics, and to gear up to have the right tools to do this. So the first question we did set to us is, what can we say about W0? So this is which work that appeared together with Julian and Andreas in July. So, and I love this picture. What I'm showing you here is basically the distributions that we see for W0, where W0 is defined as such, some normalization factor. You normalize it. It's a gauge invariant essentially because you're rescaling with the Kähler potential, and this is showing you for this now for different geometries. Yeah, so these are geometries with 2 complex structure moduli, 3 complex structure moduli, 4 complex structure moduli, 5 complex structure moduli, each having something like, you know, at least 10 to the 5 or 10 to the 6 data points in. Yeah, and so now we can actually look at these ensembles and see how are they distributed in the what we do look at. And what is exciting is first of all, okay, so these are all at the same scale. Yeah, so these graphs are not kind of rescaled at all. So if you ever wondered about, you know, so this looks pretty universal, I would say, yeah, across geometries, and I was not you know. This is obviously something that people were thinking about, you know, that this would appear. Well, we can now look at it and see, you know, how universal is this, and see what are these structures. And you know, we can explicitly look, okay, yeah, what is going on, and yeah, that clearly, you know, connects with these works. So we want to understand this a little bit of what is going on. So now, as you know, there's in the literature we do see that there should be a Gaussian distribution. So you can ask, you know, how well does a Gaussian distribution fit this? So here I'm showing you the absolute value. So if you take an absolute value of a Gaussian in 2D, this is the distribution that you would get. It's a Rayleigh distribution, and you see this here for different standard deviations. And you can fit this to our data. You see clearly some deviations that do happen. So we have this kind of universally, there's some, you know, underfit, there's some overfit, and that's something we can study. We can see how well, you know, how far away are we from these, etc. across geometries. But nevertheless, the Gaussian is, at least for these ensembles that we do look at, a reasonably good fit. Now, this becomes important if we are starting to talk about things about the expectation for the smallest W0 in your ensemble. So if you think about a two-dimensional Gaussian and you know, take samples from it, you can ask, okay, what is the minimal value for W0 that you would be expecting? If you do this for a Gaussian at varying standard deviation, you see this kind of behavior. And so what does this tell you is that if you want to get hierarchies by just randomly just drawing from this Gaussian, you basically have to go to really, really large sample sizes, right? So this is something which is not feasible, right? So if you want to get something like 10 to the minus 10 in terms of W0, you would need to get to really, really huge sample sizes. So what this is important because now this is, you know, also, you know, our results are very much consistent with this, so they lie in the kind of expected range here. What we do need in order to find W0 here numerically, small values of these hierarchically suppressed one, is to do some more dedicated searches. Yeah, we need to not just randomly sample, but we need to have some algorithm. We need to have some machine learning procedure. I'll show in a minute about what to do in order to, you know, hierarchically suppress the and efficiently sample with no W0. And I think that is very exciting, yeah, to do this, because then you know, we can actually look at what is out there. And I think this is the same story as if you were to as if you were to randomly sample from pixels to get images of cats and dogs. That's the same story here. Now, let me talk a little bit about supersymmetry breaking vacua. So this is something which we put out in August then. Okay. No, I looked at the question in the chat. So there's only one question. I looked at this. Oh, okay. Good. Yeah. So let's. So can we construct SUSY breaking minima? So this is something which was proposed a long time ago, essentially by Saltman and Silverstein in this paper. And so basically, it's just using complex structure moduli. So that setup that I'm looking at and looking for general minima in this setup, not doing anything special and just looking on the 4D EFT, what is happening, right? Nevertheless, you know, this, you know, was not possible before. And so, okay, so they did this in toroidal things, but the interesting thing is, okay, let's look at some Calabi-Yau cases and see whether we can do this story. So in 2017, there was one paper which basically looked at this question in the continuous flux case, but the minima are not transferable to the discrete case necessarily. And so what we do show here now is to actually get a large ensemble with discrete for the discrete one. And now this is, again, as a to stress this, the only thing that we had to change effectively was our minimization module in this whole story. We could just reuse all of the code structure for going from the pre-potential to the scalar potential, the few lines of code, and you can get this going. Now this is a little bit more challenging on the optimization chart. So I'm showing you here samples for 2 and 3 moduli, and this is more challenging for 2 reasons. One, because it's a slightly more complicated expression that you have to minimize, and you have to also look at the Hessian a lot of the time, and obviously you're not finding minima all the time. But also what you're doing is you have to sample from a random starting point rather than from using the IST sample. But nevertheless, we can do it. So here are 10 to the 5 solutions each, and I'm plotting here their distribution with respect to the gravitino mass. And so as you can see, there's actually, it's nice to look at these samples, because now you can see that in a lot, still, quite some size of these, you have hierarchical suppressions compared to the gravitino mass. So now, if you're only looking at a few solutions, 4 or 5 or so, you might be all sitting here, yeah, as you normally would be sampling. So you would never see these things. So if you're looking at large ensembles, you would see these. And so that's an interesting observation. Now, if you want to really go to phenomenology of the CC, you obviously could do this in the sense of making more phenomenological assumptions, say, assuming things about a non-perturbative contribution for the Kähler moduli, doing Kähler moduli stabilization a la KKLT, and then you would get also a distribution for lambda effectively out. I'm not doing this here at this stage yet, because obviously there are ongoing discussions about the prefactor of these things, and you would have to make additional cuts on your geometries in order to realize these things. But I want to, these are obviously things that people look at, and in particular, the Cornell group is looking at these things and has exciting work in these directions. But so in terms of the party line, this is really something where we can be heading. And this depends on your taste, how many assumptions you want to be making. But if you're, free to go with making these assumptions, you can easily get to phenomenology. Good. Here is the distribution again of V0 and GS. You can ask now things obviously. Do you have, weak string coupling and these hierarchical suppressions? So you can still have small values and 10 to the minus 2. But you see also that in looking at these higher dimensional distributions is something which we will probably have to do, right? If we want to combine various phenomenological things, these are, high dimensional distributions. So we have to see whether both things are realizable always at the same time. Now, another interesting point to this story is that we can compare supersymmetric and non-supersymmetric vacua. So how do they differ? So now we have obviously the setup. We can run it for the non-SUSY and the SUSY case. So here's for a 2D example, and what we have to do is we have to sample in both of these cases uniformly, and you do see differences, slightly appearing in this story. So you see that the supersymmetric ones, right? So you're open with the non-SUSY ones. You are staying here, you're staying within. If you are looking at the superpotential, the distribution of this, you see differences, right? You see differently a different structure appearing here between the supersymmetric and the non-supersymmetric case. And interestingly, also when you're looking at here is essentially the tadpole contribution plotted. And here is W0 as a contribution. So if you're looking at the supersymmetric sample, you see a clear boundary of where you are, which scales as the square root of n flux. And so the contribution to n flux is here on the x-axis. Now, if you're looking at the non-supersymmetric ones, we don't see this happening at all. We see a population going in here as well. So there are differences which we can study. Good. So Now you can do this whole story for multiple geometries, see how universal does this behavior hold, and we do see that this is persistent across examples. Now let's come back to the story of, you know, where do we want to take this? So we do want to take this now to basically, you know, we are in the we have realized kind of the green line here, yeah, where we are randomly sampling in these spaces. Now we want to connect back with our older work where we looked in toy examples on whether we can use machine learning to realize something like this blue curve. So what I'm showing you here are results that we did, you know, some time ago, is where we're looking at trying to generate minima which have W0 of a particular value. And this is in the case of simple conifold and toroidal examples. And what we do analyze here, or what I'm showing you here, is a visualization of this 8-dimensional space to project it down to 2 dimensions just with principal component analysis. And what you do see is that in various algorithms, you do see the emergence of these two clusters that do appear. And so this is also kind of resemblant here in the in this picture. So what we do here is we start with a random starting point, and this is in Z8, so it's 8-dimensional, and then we let it evolve. So here we use some reinforcement learning to do this, and basically what the reinforcement learning is able to do is it's allowed to change the flux quanta by 1, and it does this it learns a strategy on how to do this, and it basically, as you can see, some are constrained, some are some should be in a particular regime. And so this is something which back then, we were very happy to get running for these simple examples. Now we have the pipeline to put this into combine this with JAX vacua to make these searches for the Kreuzer-Skarke database, and to see what methods are out there, how universal are these strategies for getting certain phenomenological features. All these questions are now accessible. So we can ask across geometries, is there the same strategy of getting a small W0, by using the same reinforcement learning agent. Good. So let me conclude. So what we are using here is we are looking at the moduli space of type 2B string theory, and we have now the tools available to explore the situation with many moduli fields. And this is a situation where we are kind of in an intermediate regime between the standard few parameter models and infinitely many parameter models. This is something which is accessible with universal function approximators, and that is obviously a well-defined path. And this is, I think, very exciting, because in this framework we can look for systematically look for solutions to the cosmological constant problem. This being an example, there could be any other beyond the standard model question that you can phrase in this way. And to actually look for such solutions, we take a probabilistic machine learning approach to gain really insights into these high-dimensional distributions, and to make sure that we get out of these high dimensions the solutions that we do want to have. What we showcase here is that we have really many modular settings now under explicitly available, and we can ask now physics questions on these examples to see whether certain things are realizable, or, and that obviously connects with things like swampland kind of considerations of whether there are certain regions which are not accessible, but we can look at it from empirical samples. And this sampling is very crucial, because this really allows us then to apply all the nice machine learning technology. And yeah, with that, I would like to thank you and draw the attention to this, new master degree that we are running at LMU Munich now. So anyone that wants to do physics and AI, and you have students that you want to recommend for this, please, have this in mind. So with that, yeah, thank you very much.
Hi, thank you, Sven. So how difficult is to find minima with superpotential to 0? So have you searched for those specifically, or?
No, we have not searched for those specifically in the setup, but this is something, again, okay, yeah, not very difficult in the sense of setting this up to search for those. Again, yeah.
But they appear, I mean, in this random exploration, have you found some of those?
So in this random one, no, you don't see that. So the smallest one was like, I don't remember now. I think this was, you can look at the plots, right? So the smaller, yeah, so the smallest ones are shown here, right? So that's essentially, so we go down here and these ones as 10 to the minus 3 or so, yeah.
Okay.
I mean, we have some more, but again, so this is again also this very nice thing about this flexibility of this code, right? Because you want to ask a slightly different optimization problem, essentially, that you want to solve. And in that sense, you only have to change a little bit of the code and then to, see what's coming out.
What happens? Okay. Something else. I mean, so you use tadpole cancellation, you say, but for all of these geometries, I mean, there is like some database or something where you really have the exact tadpole, because you need to know if there are 03, 07 planes. You need this. So is this a rough tadpole, or is really?
So good. So that's it. So the one that I was showing you here, they are all with exact. They are all with exact orientifold construction.
Okay.
So we exactly know what the tadpole is. So that's an exact number, not an estimate.
Okay, but in this JAX vacua package, everything. So for all this list, you have the precise tadpole, or I would.
So good. So this is where we go. So we do an extra calculation to get this number effectively, right? So there's the work by the Cornell group essentially to which tells you, okay, certain classes of explicitly how to do the orientifold involution, or like how to explicitly construct it for these polytopes, and that's the number that you're getting out of this.
Okay.
Yeah.
Hi, so I just wanted to clarify, ask one thing I'm confused about. So initially you mentioned when computing so for the prepotential computation in LCS is clear, but you also mentioned that the sample points around the conifold. So how do you extend the periods, or do you expand the periods around those conifolds or other points outside, far away from LCS?
Oh, good. So that's still work in progress, right? To look at this, and that's an encouragement for people to provide the explicit, expressions effectively, yeah. Because okay, in some examples, right, this is known, but there's a clear step which has to be gone from one example or two examples to having a general framework to apply to general Kreutzer-Scarpe. So
thanks.
Thank you. Let's see. Well, this might be a little bit futuristic question, but suppose that this type of program is pushed far, and you find from 5-10 years from now that you have a very good scan of the string theory vacua, at least in the crossover models. And then the question is that what type of things are you going to do? So probably there are some fine-tuned points in the modular space where there is a good approximation of standard model, and if you want to push it farther to pin down a particular model, or maybe you hope that there is a very general pattern somehow, maybe not the exact property, but a little bit vague, but some general property you can extract, which you can test with experiment, or it's well, okay. I know this is a
Yeah.
tough question about string theory, but that ultimately that's a question what it
Yeah,
would
so,
do
so
with
no,
this.
but it's a really cool question. I mean, it's really cool. So in a sense, so that's why I love the W0 example, for instance, right? So because the W0 example is really a cool kind of test for this story, because now there are human-made strategies around for getting these small values, right? So Cornell Group, Munich, and so on, they have some strategies on how to align things in that. So what this program is going to give you is hopefully different solutions. Yeah, so that's different to that. And then it's very exciting to open the box and see, okay, what strategy is actually behind this.
I see.
And so there will be some mathematical framework that actually, corresponds to that strategy.
I see.
And for me, that is like, if you want to be in that kind of direction, right? That's exactly what where this is exciting. This is like, if you remember the Go kind of story, right? So at some point Go was playing a move that people were not expecting. That's what I'm looking out for here, right?
Oh, I see. So that's
because there
fantastic.
could be different strategies.
I see. So you want to highlight some particular parameter regions where things look good, and then you're proposing to study it even analytically or maybe better something. So, but a combination, and then have a better understanding in itself.
Yeah. So for instance, right, I mean, that's why I showed this plot here, right? So this is a toy thing, right? Effectively, right? So you would not naively think about that, there might be this kind of clustering or so going on. Yeah. So it's really like, okay, what mathematics is behind such clusters, and you're really solving nonlinear equations here, right? To get to these stories. They are not at all, these kind of clusters you can't see if you're just looking at the equations. Well, I can't see that. Yeah. So in that sense, that's really, telling us, okay, yeah, we kind of have to formulate a formalism to get to this. Yeah.
I see. Great. Thank you.